Imagine for a moment that you are standing in the vast, silent expanse of the Gobi Desert. The wind whispers across the dunes, carrying with it the dust of ancient history. Above you, the sky is a deep, endless blue, fading into the black of space. And somewhere up there, more than 480 kilometers above your head, a satellite is racing across the heavens at nearly 8 kilometers every second. Now, imagine that you have in your hand a single particle of light, a photon, a tiny, invisible speck of energy. You point a laser at the sky, and in an instant, that photon disappears from your hand and reappears inside the satellite, hundreds of kilometers away. You have not sent a signal. You have not transmitted a message. You have done something far stranger, far more profound. You have teleported a particle of light from the Earth to space. This is not science fiction. This is not the plot of a Star Trek episode. This is real physics, and it happened just a few weeks ago. In June of 2026, a team of Chinese scientists achieved the first-ever ground-to-satellite quantum teleportation. They beamed a photon from a station in the Gobi Desert to the Micius satellite, an orbiting laboratory dedicated to quantum communication. Previous teleportation experiments were limited to distances of about 100 kilometers due to photon loss in optical fibers or terrestrial free space channels. This experiment shattered that barrier, opening a new chapter in the history of physics. To understand what they did and why it matters, we have to go back to the very beginning. We have to talk about one of the strangest, most counterintuitive, and most beautiful ideas in all of science: quantum entanglement. Let me take you back to 1935. Albert Einstein, the greatest physicist of his generation, was deeply troubled by the emerging field of quantum mechanics. He had, in fact, been one of its founding fathers. But the more he looked at it, the more he hated it. He hated the randomness. He hated the uncertainty. And most of all, he hated what he called spooky action at a distance. The idea that two particles, once they have interacted, could remain connected in such a way that measuring one instantly affects the other, no matter how far apart they are. It violated his deep-seated belief in locality, the idea that nothing can influence anything else faster than the speed of light. Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, published a paper that was meant to expose the absurdity of quantum mechanics. They proposed a thought experiment that would show that quantum mechanics must be incomplete. If two particles are entangled and you measure the position of one, you instantly know the position of the other, even if it is on the other side of the universe. This, they argued, was impossible. There must be hidden variables, unknown properties that determine the outcome of the measurement. Quantum mechanics, they said, was not a complete description of reality. For 30 years, this was a matter of philosophical debate. Then, in 1964, a brilliant physicist named John Bell came up with a way to test Einstein's idea. He derived an inequality, a mathematical statement that would be true if local hidden variables existed, and false if quantum mechanics was correct. And over the next few decades, experiment after experiment showed that Bell's inequality was violated. The universe, it turned out, is indeed spooky. Entanglement is real. Particles can be connected across vast distances, and measuring one instantly affects the other, faster than the speed of light. Einstein was wrong. Quantum mechanics was right. Now, entanglement is not just a curiosity. It is the foundation of a new kind of technology. It is the key to quantum computing, quantum cryptography, and, most excitingly, quantum teleportation. Let me explain what quantum teleportation actually is, because it is not what you see in the movies. In Star Trek, a person is disassembled atom by atom, and their atoms are beamed across space and reassembled. That is not what happens here. Quantum teleportation does not transport matter. It transports information. It takes the quantum state of a particle, all the information that defines what that particle is and how it behaves, and transfers that information to another particle, creating a perfect replica. The original particle is destroyed in the process, but its quantum state, its essence, is reborn somewhere else. Here is how it works. You have three particles. Particle A is the one you want to teleport. Particle B and particle C are entangled. You take particle A and particle B, and you perform a special kind of measurement on them, a Bell state measurement. This measurement entangles particle A with particle B, and in the process, it destroys the quantum state of particle A. But the information about that state is now encoded in the entanglement between particle A and particle B. Because particle B is entangled with particle C, the information about particle A's state is also transferred to particle C, but it is scrambled. It is not yet a perfect copy. To complete the teleportation, you need to send a classical signal, a regular, old-fashioned message, from the location of particle A and B to the location of particle C. This signal tells you what transformation to apply to particle C to unscramble the information and recreate the original quantum state. Once that transformation is applied, particle C becomes an exact replica of particle A. The original is gone. A perfect copy has been created elsewhere. This is the magic of quantum teleportation. It relies on entanglement, on the spooky connection between particles, and on classical communication to complete the process. And it works. Scientists have been teleporting photons and atoms over short distances for years. But teleporting a photon from the ground to a satellite is a whole different ballgame. The Chinese team, led by physicists from the University of Science and Technology of China, used the Micius satellite, which was launched in 2016 specifically for quantum communication experiments. Micius carries a special payload, a source of entangled photons, and a receiver capable of detecting single photons with exquisite precision. The ground station in the Gobi Desert was equipped with a powerful laser and a sophisticated optical system to track the satellite as it passed overhead. The satellite and the ground station had to be perfectly aligned, with an accuracy better than a fraction of a degree. The photon had to travel through the turbulent atmosphere, through layers of air with different temperatures and densities, and arrive at the satellite without being absorbed or scattered. It is like hitting a moving target the size of a coin from a distance of 480 kilometers, while the target is moving at 8 kilometers per second. And they did it. They successfully teleported a photon from the ground to the satellite. They transferred its quantum state from one location to another, across a distance that was previously unimaginable. This is not just a technical achievement. This is a fundamental step towards a global-scale quantum internet. Imagine a world where information is transmitted not as signals that can be intercepted, but as quantum states that cannot be copied or measured without being destroyed. A quantum internet would be absolutely secure. Any attempt to eavesdrop on a quantum communication would be immediately detected because the act of measuring a quantum state changes it. This is the basis of quantum cryptography. And quantum teleportation is the mechanism that allows quantum information to be transmitted over long distances. Without teleportation, quantum signals would be limited by the loss of photons in optical fibers. With teleportation, you can create a network of quantum repeaters, nodes that can receive a quantum state, teleport it to the next node, and so on, over arbitrarily long distances. This is what the Micius experiment has demonstrated. It is the first step towards a quantum internet that could connect the entire planet. But wait, there is more. In the same month that the Chinese team achieved ground-to-satellite teleportation, another team of physicists reported a different kind of breakthrough. They created the first fully distributed tripartite entangled state, a three-particle entangled state known as a Greenberger-Horn-Zeilinger (GHZ) state, across a network of three individual atomic memories. This is significant because it is the first time that a three-particle entangled state has been created between individual atomic qubits that can be individually controlled and detected with high fidelity. Previous experiments had created GHZ states between solid-state qubits or atomic ensembles, but not between individual atoms. This new achievement opens the door to modular quantum computers, distributed sensing, and multi-party secure communication protocols. It is the foundation of a quantum network that can connect multiple nodes, not just two. And then, there is the strange metal. In another study published in June 2026, physicists at Rice University and TU Wien measured the quantum entanglement of a quantum-critical metal. They found that in these highly collective materials, electrons are particularly highly entangled, losing their individual identity and acting as a single, coherent whole. This is not just a curiosity. It is a new way of understanding collective states of matter, and it could lead to new capacities for quantum information. The electrons in a strange metal are entangled in a way that is fundamentally different from the entanglement of photons in a teleportation experiment. But it is the same underlying phenomenon. Entanglement is everywhere. It is the glue that holds the quantum world together. Now, let me bring this back to Richard Feynman. Feynman was a man who was fascinated by the strange, the counterintuitive, the seemingly impossible. He once said, "If you think you understand quantum mechanics, you don't understand quantum mechanics." He would have been utterly captivated by the idea of quantum teleportation. He would have loved the thought experiment, the idea that you can take a particle, destroy it, and recreate it somewhere else. He would have asked the questions that we should all ask. How does the information get transferred? What happens to the original particle? Can we teleport larger objects? Can we teleport a person? The answer to that last question is, unfortunately, no. Not anytime soon. Quantum teleportation works for particles, for individual photons and atoms. It does not work for complex objects like people, because the amount of information required to describe a person is astronomically large. There are more atoms in a human body than there are stars in the observable universe. Teleporting a person would require measuring and transmitting the quantum state of every single one of those atoms, and that is far beyond our current capabilities. But the principle is the same, the physics is the same, the strange, spooky connection between particles is the same. And that is the beauty of physics. The same fundamental laws that govern the behavior of a single photon in the Gobi Desert also govern the behavior of electrons in a strange metal and the behavior of atoms in a quantum network. The universe is a vast interconnected web of quantum states, and we are just beginning to learn how to manipulate them. We are just beginning to learn how to teleport, how to entangle, how to build a quantum internet. This is the spirit of Feynman's Curiosity Lab. We do not just learn about the universe. We play with it. We ask the big questions. We build the experiments. We push the boundaries of what is possible, and sometimes we achieve something that was once considered impossible. We teleport a photon from the Earth to a satellite. We create a three-particle entangled state. We measure the entanglement of a strange metal. And we realize that the universe is even stranger, even more beautiful, even more wonderful than we ever imagined. So, the next time you look up at the night sky, think about the Micius satellite. Think about the photon that traveled from the Gobi Desert to space, not as a signal, but as a quantum state. Think about the entanglement that made it possible, the spooky connection that Einstein found so distasteful. Think about the future that this technology is building, a future of secure communication, of quantum computers, of a global quantum internet. And remember that we are living in a golden age of discovery. We are the generation that is learning to teleport. We are the generation that is building the quantum future. This is Feynman's Curiosity Lab. Stay curious. Keep asking why, and never stop exploring. The universe is full of magic, but it is a magic that we can understand, a magic that we can control, a magic that is real, and that is the most magical thing of all.